Imagine waking up to a sunrise, but instead of golden light breaking over a peaceful horizon, you look up and watch clouds of molten rock slowly materialize out of thin air. Not rain clouds, not snow clouds, rock clouds. And by the time the sun sets on the other side of the sky, they vanished completely, dissolved back into the scalding atmosphere as if they were never there at all. This isn't science fiction. This is a real planet. And the James Webb Space Telescope just pulled back the curtain on it in ways we never thought possible. Welcome to one of the most alien worlds ever studied in the history of astronomy. A place so extreme, so wildly different from anything in our solar system that it forces us to completely rethink what we even mean by the word weather. Today, we're diving deep into the discovery of WASP-107b, a planet where the atmosphere behaves like nothing science has ever seen before, and where Webb's revolutionary infrared eyes caught something that left astronomers genuinely stunned. To understand why this discovery matters so much, we need to set the stage. WASP-107b orbits a star about 200 light-years away from Earth, in the constellation Virgo. It's what scientists call a hot Neptune, or more dramatically, a super-puff planet. That second name alone should tell you something. WASP-107b is roughly the size of Jupiter, but it has the mass of only about 1/3 of Neptune. What that means is that this planet is extraordinarily low density. If you could find a bathtub large enough and somehow filled it with water, WASP-107b would float. It is, in every sense, a cosmic cotton ball, a gas giant so fluffy and diffuse that it barely seems like it should hold together at all. And because it's so puffy, because its gravity is relatively weak and its atmosphere stretches out like a vast, loosely packed envelope, it turns out to be the perfect laboratory, the perfect planet for a telescope like Webb to peer into and read like an open book. Here's how Webb does it. When WASP-107b passes in front of its host star, an event called a transit, some of that starlight filters through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb different wavelengths of that light, and Webb, with its extraordinary sensitivity to infrared wavelengths, can decode that absorbed light like a fingerprint. This technique is called transmission spectroscopy, and Webb performs it better than any instrument humanity has ever built. So what did Webb find when it turned its golden mirror toward this cosmic cotton ball? Scientists expected to see sulfur dioxide. They expected water vapor. They expected some carbon dioxide. And they found all of those things. But then, hiding in the data, was something completely unexpected. Something that made the team do a double take. Webb detected silicate clouds. And not just any silicate clouds. These were clouds made of tiny sand-like particles.
Essentially, clouds made of rock. Now here's where it gets truly mind-bending. When the research team began modeling how these clouds could exist and why they seemed to behave differently on different sides of the planet, they uncovered a cycle so bizarre, so utterly unlike anything in Earth's experience that it borders on the surreal. WASP-107b is tidally locked to its star. That means one side of the planet always faces the star, roasting in permanent, relentless daylight, while the other side sits in permanent, freezing darkness. The temperature difference between these two hemispheres drives ferocious winds that roar around the planet at thousands of kilometers per hour, creating a massive circulation system. On the hot day side, the temperatures are so extreme, we're talking over 1,000 degrees Celsius, that silicate materials, the rocky stuff that forms the crusts of planets like Earth, simply vaporize. They become gas. Silicon and oxygen atoms drift upward into the atmosphere as invisible vapor. But as those winds carry that vapor toward the cooler boundary regions, toward the terminator line, the great twilight zone between day and night, something remarkable happens. The temperature drops just enough, and those silicate vapors begin to condense. They crystallize. They form tiny, glassy, sand-like particles, clouds, rock clouds. Silicate clouds forming at the planet's eternal dawn, catching the light of a sun that never moves in its sky. And then those clouds, carried further by the winds into the dark side of the planet, begin to fall. It rains. It rains sand. It rains silicate droplets falling through a pitch-black sky on the night side of an alien world. Those droplets sink deep into the lower atmosphere, where the heat rising from below vaporizes them once again, and the cycle starts over. Vapor rises, gets swept to the dawn terminator, condenses into clouds, drifts to the night side, rains back down, vaporizes, rises again. An endless churning rock weather cycle that has been running for billions of years. Let that sink in for a moment. On Earth, our weather is driven by water, by the evaporation of oceans and the falling of rain. It is the engine of life on this planet. But on WASP-107b, the same fundamental process is playing out. Evaporation, condensation, precipitation, except the substance isn't water, it's rock. The mountains of Earth, the cliffs, the canyon walls, the very material we consider the ultimate symbol of permanence is a weather system on another world. And here is the perspective shift that I want you to carry with you after this video. We tend to think of planets as static, finished things, balls of rock or gas just sitting there in space. But what Webb is showing us, what WASP-107b is screaming at us, is that planets are dynamic, churning, endlessly active systems. The atmosphere of this world is not a passive wrapper. It is a machine.
A geological machine running in the sky, cycling rocky material the way Earth cycles water. And if that's possible on WASP-107b, what else might be possible on the thousands of other exoplanets we've yet to study in this kind of detail? This discovery also tells us something profound about the power of Webb itself. Prior to Webb, we could detect that planets like WASP-107b existed. We could measure their size, their mass, their orbit, but the inner workings of their atmospheres, the chemistry, the cloud dynamics, that was largely a mystery wrapped in darkness. Webb changed that overnight. In a single set of observations, it identified not just what chemicals are present in this planet's sky, but how those chemicals behave, how they move, transform, and cycle. We went from knowing a planet exists to understanding its weather in one extraordinary leap. And this is just the beginning. The WASP-107b results, published in the journal Nature, were celebrated not just as a discovery about one exotic world, but as a proof of concept. A demonstration that Webb can do atmospheric science on distant planets with a level of precision we once reserved for studying worlds in our own solar system. The implications are staggering. Rocky, potentially habitable exoplanets are next on the list. Webb is already gathering data on some of them. And if it can reveal silicate rain cycles on a gas giant 200 light-years away, what might it find in the atmosphere of a world more like our own? The cosmos is not a quiet, static gallery of objects hanging in the dark. It is alive with processes, with cycles, with weather and chemistry and geology, happening on scales and in forms we are only just beginning to comprehend. WASP-107b is one data point in what will become an atlas of alien worlds, each one stranger, more wondrous, and more scientifically precious than the last. If this blew your mind even a little, do me a favor, hit that like button. It genuinely helps this channel reach more curious minds just like yours. Subscribe if you haven't already, because we are just getting started on this journey through the cosmos. And drop a comment below. I want to know, what kind of alien weather do you think Webb will discover next? Methane snow? Iron rain? Something we haven't even imagined yet? Tell me your wildest guess. Next time, we're going somewhere even more extreme, a place where the laws of physics themselves seem to buckle under the weight of what exists there. You do not want to miss it.